Kia ora, Robert McLaughlin here. Welcome to Lecture 2 of Week 11. Today we're going to look at nonlinear systems as models. They'll both be planar, so two-dimensional systems, and we'll want to understand what the model is telling us, what it's describing, and then use the techniques that we've learned to understand the system as much as we can. And the first example is called the Pendulum Equation. First, I'm just going to derive where this equation comes from before we analyze it. Here's the pendulum equation. So imagine a pendulum swinging back and forth, and it's got a solid rod, and it's got a bob on the end of mass m, and we're going to describe it in terms of its angle from the vertical down position, theta. As it swings back and forth, it's going to describe a circle. So I'll call that distance along the circular arc x, and I'll call the length of the solid pendulum rod L. And now we're going to look at the forces acting on the pendulum, of which the force we're going to consider is gravity. So there will be a vertical down force equal to mass times acceleration due to gravity, g. That's the setup. Now, what do I do with this setup? The component of that force along the pendulum rod will just contribute to the tension along that rod, so I'm not really interested in that. So I want to take that force and decompose it into two components. This angle here will be theta again, which means that the component of the force that's acting to affect the actual motion of the pendulum will be this bit here, which is going to be it's going to be mg sine theta. And the way I've got the set up here, it's going to be pointing in the negative direction, so negative mg sine theta. Now from the diagram there, comparing x and theta, I've got x is equal to L times theta. So differentiating with respect to t, I get x dot is L theta dot, x double dot, the second derivative of x is L theta double dot. Then I use Newton's second law, force equals mass times acceleration. So mass times acceleration, which is x double dot, which is L theta double dot. Mass times acceleration is equal to force, which is minus mg sine theta. Simplify that, I get theta double dot plus g over L sine theta equals 0. That's the pendulum equation. Analyze the forces. Write down the differential equation. G and L are just constant parameters. Now that's a second order differential equation, so I want to rewrite it as a first order system by introducing a new variable y, and that's going to be the angular velocity, the rate of change of angle with respect to time. So I define my new dependent variable y to be equal to d theta dt, and then I can get an equation for dy dt from dy dt equals d squared theta dt squared, which is minus g over L sine theta. So now I have a system of two first order nonlinear differential equations. It's nonlinear because of this sine theta term here. So how do I analyze this nonlinear system? First thing we're going to do is find the fixed points. That's where the right hand side is equal to 0. So I take the right hand sides and set them equal to 0. So that means y is going to be 0. That's the first right hand side. And sine theta is going to be 0. That means theta is in pi, any integer multiple of pi. Now angles of course are not unique, so we've really only got two different fixed points. There's theta equals 0, which is the vertical down position, and theta equals pi, which is the vertical up position. So I've really got two geometrically distinct fixed points. So, using what we've learned so far, I can try and analyze the stability of those fixed points by linearizing the system at each fixed point. That means I first need to write down the Jacobian derivative. The derivative of this one with respect to theta is 0. With respect to y is 1. The derivative of this one with respect to theta is minus g over L cos theta, and with respect to y is 0. That's my Jacobian derivative. And now I take each fixed point, theta equals 0, y equals 0. The Jacobian derivative, that's the vertical down position, is 0, 1, minus 1, 0. Find the eigenvalues, and you find they're equal to plus or minus I. That means the linearized system is a center, but because the real part of that eigenvalue is 0, unfortunately, this doesn't tell me anything about the behavior of the nonlinear system. So the linearization, because the real part of the eigenvalue is 0, the linearization does not determine the phase portrait of the nonlinear system. Never mind, let's press on. Now we'll do the vertical up position. Theta equals pi, y equals 0. There the Jacobian is equal to 0, 1. I see I forgot the g over L. Let's just take g equals L equals 1 for the purposes of illustration. Then I get 0, 1, 1, 0. Now lambda is equal to plus or minus 1. There's one positive and one negative eigenvalues. That means the vertical up position is an unstable saddle. Now it's no surprise that the vertical up position for a pendulum is unstable. But we have learned something new, namely it's a saddle point. That will be important later on. Now here we see a blank page. That's because I'm going to need a new idea. Because my vertical down position was had pure imaginary eigenvalues, I don't actually know what the phase portrait is going to look like that nearby. I'll need something else. And what that something else is a very cunning little trick, which I will show you now, which is to eliminate the t variable by computing d theta dy. Using the chain rule, that's equal to d theta dt divided by dy dt. That's just a rearrangement of the chain rule. That is equal to y divided by minus g over L sine theta. And this is a differential equation that I can solve because it's just a single separable first order equation. Let's separate variables. I get minus g over L sine theta d theta is equal to y dy. Integrate both sides. G over L cos theta is equal to a half y squared plus a constant, and I'm just going to choose to call the constant minus a half k just for convenience. So therefore this quantity y squared minus 2g over L cos theta is equal to k. It's a constant. Which means that if I just draw the level sets of that quantity, I will have some curves in the plane, and they must be the solution curves, the phase space curves of the system. Now, not every system will be amenable to this technique, but when it does work, it's really good. And it works for a reason, and the reason is that there's a physical basis to this conserved quantity. K is the total energy of the system. In fact, I think half k is the kinetic energy. Kinetic plus potential energy. So this is an example of a conserved quantity, or also called a first integral of a differential equation. So here we've used MATLAB to draw some level sets of this function for 3 different values of the kinetic energy. K equals 0, we get the red curve there. That's a closed oscillation. That just corresponds to the pendulum swinging back and forth and back and forth forever. It's a periodic orbit. The green one is when k equals 2. It's actually 2 different orbits there, because this is the point pi 0. This is the vertical up position. This is also the vertical up position. And this says, the green orbit says that if you start near the vertical up position, you will fall down, pass through the bottom, and return to the vertical up position. You see the angle increases from minus pi all the way around to pi. It will slow down and approach the vertical up position again. And as you increase the energy further to the blue curve, k equals 5, that corresponds to a solution where the angle is just constantly increasing. The pendulum is just going round and round and round, speeding up and slowing down as it does so. This means that the fixed point at the vertical down position at theta equals y equals 0 is in fact stable, because it's surrounded by periodic orbits. Not circles anymore, but they're periodic orbits of slightly different periods corresponding to different amplitude oscillations, which means that if you start nearby, you do stay nearby forever. So we have learned that theta equals y equals 0 is a stable center. So a combination of techniques there, bit of calculus, bit of differential equations, bit of geometry, drawing the phase portrait, allow us to get a pretty full understanding of a complicated nonlinear system. Okay, next example. Now we're going to look at 2 examples of population modeling for 2 species. So I'm going to have a species big X with population X of t, and a species Y with population Y of t. And let's suppose these are the differential equations that they obey. What does this mean? Well, let's look at the X equation first. If Y was 0, if species Y wasn't there, and notice that Y equals 0 is actually a fixed point, if Y wasn't there, then I'd have x dot equals x times 4 minus 2x. That would be the logistic equation. So that means if species Y isn't there, the population X, if it starts smaller, will increase with a rate constant of 4 until it reaches its capacity. Same thing with the second equation. If species X isn't there, then species Y wants to increase until it reaches its capacity. So I've got 2 populations, each obeying a logistic equation, and then I've got the interaction term, which says what happens if they're both present. Here's an interaction term, and here's an interaction term. This says that if some y's are present, then the growth rate of x will decrease. And this one says if some x's are present, then the growth rate of y will decrease. In other words, X and Y are competing species. So this is a model of 2 species in the same environment that are in direct competition with each other. How do I understand this nonlinear differential equation? Let's find the fixed points. Each right-hand side is written in factored form, which means there are 2 choices when I set either of them to be 0. So I can get the fixed points at x equals 0 for the first one. If x equals 0, Then the second one says either y equals 0 or y equals 3. Or if in the second one y equals 0, I already know that x equals 0 is a possibility. Plug that y equals 0 into the first equation, you get that you have another solution when x is 2. Or both of the second factors could be 0, which would mean that 2x minus 2y is 4, 2x plus 2y, 6x plus 3y is 9, and the solution is x equals y equals 1. So altogether there are 4 fixed points. So now I could work out the Jacobian, plug in the x and y for each of the fixed points, and work out what type of fixed points I have. I'll just write down the answers here. At fixed point 0, 0, that's where both species are locally extinct, I get lambda equals 9 and 4, so that's an unstable node. At 0, 3, so that's when I've got some y's but no x's, then lambda is minus 9 and minus 2, so that's a stable node. 2 negative real eigenvalues. When x is 2 and y is 0, so when I've got some of species x but no y's, then lambda is minus 4 and minus 3, again a stable node. And when both species are present, the fixed point there is 1, 1, so 1 unit of each species, then lambda is minus 6 and 1, 1 negative, 1 positive. That means it's an unstable saddle. So here I have a unstable source or unstable node. That means if I start close to 0, so start with small numbers of both x and y, then they'll both grow. This is a stable node. That means if I've got a steady population of y's and no x's, then that's a stable situation. Same thing the other way around. But if I have both of them present at their steady state, 1 unit of each, that is an unstable saddle. So that suggests in reality I am not going to see a stable coexistence of both of these species because of the way they compete with each other. So to do more, I can draw the face portrait, which here has been done numerically. Here is the face, here is the fixed point at 0, 0. Everything moves away. That was the unstable node. Here's the fixed point at 1, 1. That was the saddle. 0, 3 and 2, 0. So I can see I have some special orbit that looks a bit like this, where I fall in there, but then move away. So whether I end up with all y's and no x's, or all x's and no y's, will depend on the starting population. If I start anywhere to the right, say out here for example, I'll end up with 2 x's and no y's. If I start over here, I'll end up with no x's and 3 y's. So quite complicated behavior from a simple model of 2 competing species. Now let's change the parameters in a very similar type of equation. Again, a population model, x dot equals x times something, y dot equals y times something. But now I've changed the coefficients. And this will turn this into a model for a predator-prey system. You can see that more y's will decrease the growth rate of the x's. More foxes means fewer rabbits. But in the y equation, more x's means greater growth rate of the y's. More rabbits means the foxes can increase. Furthermore, if x is 0, so there are no rabbits, then the y equation reads y dot equals minus 2y. So without the rabbits, the foxes will just die away to zero very rapidly. So let's repeat the same calculation as before. We find 3 fixed points this time. The fixed point at 0, 0 has lambda equal -2 and 1. This time it's a saddle. The fixed point at half 0, that's where there are some rabbits but no foxes. That has lambda equals ±1. That is an unstable saddle. And the fixed point at 1/3, 1/3 has lambda equals -1/3 ± I root 5 over 3. That is a stable spiral. So this time we have some possibility of coexistence of the two species because of this stable fixed point when there is 1/3 unit of rabbits and also 1/3 unit of foxes. Let's see how that analysis compares to the phase portrait, which has been drawn numerically. Yes, sure enough, here we see a saddle where I can move down this way. That represents no rabbits and the foxes dying out. Away this way, that means no foxes and the rabbits increase without limit. But if I have rabbits and foxes, then I undergo a spiral. And in this case, I quite rapidly move in towards the stable fixed point, but with some oscillations. The population numbers will fluctuate a bit until it settles down to the steady coexistence. So with this class of differential equations, as you change the parameters, you can get very different kinds of behavior coming out of the system. And this is a big area of study called predator-prey systems. And here's a famous bit of data that was collected in the 19th century in northern Canada when they were doing lots of trapping. They were trapping 2 species, hares and lynx, so they had very good data for how many of each they were catching. They weren't trapping enough to affect the overall population, which was just undergoing natural cycles. And you see that both populations are very cyclical. And it's not quite as clean as in the model, of course, but roughly speaking, there's a population explosion of hares, lots of hares. That lets the lynx population grow to a peak. Then the hares start getting wiped out and they die down by an enormous factor, like to 1% of what they were. Then the lynxes die out and then the cycle repeats. So even a simple model can reproduce quite complicated dynamical phenomena in nature.